Alright, thanks for watching. And today we want to do something really cool. Namely, we want to figure out what are the most important properties that characterize a determinant. And in fact, they're as follows. So we'll do it in form of this game. So let delta be the following function from n by n matrices to the real numbers that satisfies the following property. So be a function that satisfies the following properties. And by the way, bear with me, I am improvising here. I haven't prepared for this, but I do want to do it. So that satisfies the following properties. First of all, delta is multilinear. Namely, multilinear just means linear in every row. So if you have a matrix of the form A1, AR minus 1, U plus KV, AR plus 1, AN, then in each row it's linear. So that would mean it's delta of A1 up to AR minus 1 U, AN plus K times delta of A1 V AN. So in every row you can just do linearity on every row. And next property, it's called alternating. Which just means that if you have two adjacent rows, so rows that are next to each other, that value is just 0. So A1, U, AN, U, it's 0. And lastly, delta at the identity matrix is 1. So suppose you have those three properties, then the claim is delta, it's nothing else than the determinant. Which is a complete characterization of the determinant function. And I'm not going to show all of it, like the details of it, because it's just repeat of the previous videos I've done. But I will show you sort of the main steps. First of all, what we would like to show, let me just see, what we would like to show first of all is using this alternatingness and this multilinearity, I want to show the property that if you switch two rows of A, you just get minus of the original function. So delta of the new matrix is just minus delta of the old matrix. So fact. So if you interchange two rows of A to get B, then delta of B, it's minus delta of A. And let me just sketch it. So first of all, suppose the rows are adjacent. So in particular, suppose you want to calculate delta of A1, I guess AR plus 1, AR, AN. Suppose you want to show that it's minus delta of A1, AR plus 1, AN. So let's first show this. If you interchange two adjacent rows, then you get minus delta. So delta of the new thing is minus delta of the old thing. And the reason is, it's kind of cute. You consider the following thing. So AR plus 1, and then AR plus 1, up to AN. Well, notice two adjacent rows are equal. So by definition, so by property 2, this value is 0. On the other hand, you can just use multilinearity. So this becomes delta of A1 up to AR. AR plus AR plus AR plus 1. AN plus delta of AR plus 1, AR plus AR plus 1, and everything else is the same, and that is delta of AR, AR, because now you can use multilinearity again, plus delta of AR, AR plus 1, plus delta of AR plus 1, AR, plus delta of AR plus 1, AR plus 1. And in particular, notice those two rows are adjacent, so delta is 0. Also here, the adjacent rows are identical. And then, what is this? This is precisely the right-hand side. And this is precisely the left-hand side. So what you get in the end is that the right-hand side plus the left-hand side is 0. So in particular, the left-hand side, it's minus the right-hand side. So this is now, so in other words, if you interchange adjacent rows, you get a minus. And then it follows in the general case. So if you have something like that, delta of AR here and AS here, then what you do, you just do a bunch of single interchanges. So that I guess AS comes to this row, sorry, or I guess AS comes right below the ARth row, and then you interchange AR for this to go to the S entry, and it turns out the signs exactly match, that in the end you get a minus. It becomes something like, I think, minus 1 to the S minus R plus S minus R minus 1, and then you get this. So, alright, so this is true, and then we also want to show something else. So we know that two adjacent rows, you know, if you have two adjacent identical rows, then delta is 0. Well, it's also true if you have any two identical rows. So that's one thing, and then, so if delta has two, I guess if A has two identical rows, then delta of A is 0. And the reason is just as follows. So suppose here we have AR, and then suddenly we have another row of the form AR. So just interchange this AR so many times until it becomes here. And all this does is just puts a minus, possibly, in front of this delta. But this delta of this matrix, by definition, it's 0. So what do we get? We get delta A is like plus or minus 0. And then in the end, we get delta A is 0. So this is two cool facts. So if you interchange two rows, you get a minus. If you have identical rows, no matter where they are, you get a 0. And that's first of all. So that's just some general properties. And then just like before for the determinant, we would like to see what happens if you do row operations to the determinant. Or I guess if you do row operations to delta. And remember, there are 3 of them. So row ops. So first of all, if you interchange two rows of A to get B, then delta of B is minus delta of A, and this we've literally just shown before. Then the second row operation, if you multiply one row of A by K to get B, then delta of B, it it's k times delta of A. So, in other words, if B looks like this, A1, dot, 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 KAR, AN, well, then, and you know, A is A1 up to AN, then delta B, that is delta of A1, KAR, AN. But the point is, then you can just use multilinearity to pull the K out. So this would be K times A1 up to AN, which is K times delta of A. So this is true, and the most interesting thing, if you add a row, a multiple of one row to the other one, it doesn't affect the determinant. So if you add K times one row of A to another one, to get B, then the determinant is the value of delta is unchanged because we don't know if it's a determinant yet. And here's the proof. So suppose B is just A, but you add, let's say, K times row R to S. So A1 and then AS plus KAR up to AN. Then you can just use multilinearity. So this is delta of A1 dot 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 AS AN plus K times delta of A1. Then AR is somewhere here, another AR by this, and then AN. But look, now delta has two identical rows. So, the matrix has two identical rows, so delta is 0, and what you're left with is simply delta of the matrix A. So in other words, the most important row operation doesn't do anything to the determinant. All right, and then, we're almost there. So just a couple of things, because basically the approach of the proof is the same thing as before. You want to use some elementary matrix business. So first of all, let's get rid of the fact where A is not invertible. So another fact. If A is not invertible, then delta of A is 0. And the proof of this is exactly the same as in the video about determinant of A inverse, because if A is not invertible, its rank is strictly less than the size, so one of the rows is a linear combo of the other ones. Assume without loss of generality is the first one, then delta of A, it's simply delta of, again, some linear combo of the other rows, so I guess C2, A2, plus dot 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 plus Cn, An, A2, dot 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 up to An, and that is C2 by linearity, multilinearity of A2, dot dot up to An, plus blah blah blah, plus Cn delta of An up to An. So this cancels out, and this cancels out. Everything else in between cancels out, and you get 0. So in other words, and I guess that this will be important for the proof, but if A is not invertible, then delta A is 0, but also the determinant of A is 0 by using the definition of the determinant. So the point is, if A is not invertible, then we do get that delta A equals to the determinant of A. All right, that's one thing. And then, let's see. All right, so I did. Right? It's a bit different orders, but we did row operations, we did non-invertibility, and now let's see what happens to our elementary matrices. And again, all this stuff is important because we know what row operations do to it, we know non-invertibility, and then lastly, let's see if we have an elementary matrix. And careful, well, I mean, I guess we know that delta of identity is 1, so no, don't be careful. So there are 3 types, right? So there's type 1, which is interchange 2 rows. Two rows, which is, think this, E is 0, 0, 1, 0, 1, 0, 1, 0, 0, and I'm claiming for this one, delta of E is 1. I guess minus 1, sorry. And the reason is, what is the interchange 2 rows matrix is just the identity, except you interchange the ith and j rows of that matrix. So in other words, if you interchange those 2 rows, you get the identity. So in particular, what does that say? It says that, so if you interchange, you get minus. So minus delta E is the value of delta at the identity, which is 1. So delta of E is minus 1. Because again, if you interchange 2 rows of E, you get the identity, and interchanging gives you minus, so you have minus 1. So that's type 1. Now type 2, it's add k times one row to another one. And by the way, the important thing is, this is the same as the determinant of E. Because also the determinant of the interchange matrix is minus 1. So 1 k times one row to another. So for example, E is, let's say lambda, I guess k, 0, 0, 0, 1, 0, 0, 0, 1. Then delta of E is just k. And that's because delta of E, by multilinearity, this is k times delta of the identity, which is k. And lastly, type 3, add k times one row to another one. Think, for example, here E is, let's say, 1, 0, 0, 0, 1, 0, k 0, 1. And in that case, all you do is take delta E, and if you want, subtract k times the first row to the third row, which doesn't affect neither the determinant nor the value of delta. And what you're left with is just delta of the identity, which is 1. So in this case, delta of E, it's 1. And again, just as before, the whole point is, what is the point? So the point is, we want to figure out what delta is. Now, we have this beautiful fact that may be underplayed a bit, but it is true that delta is the determinant on those elementary matrices. So the question is, what about general matrices? Well, it will just follow because any invertible matrix can be written as a product of elementary matrices. All right, and we're almost done. So just 2 more facts. First of all, let's show multiplicativity. So another fact, almost done. So delta AB, it's delta A times delta B And the proof is almost identical to the one with determinants. So basically, first of all, you do the case that A is not invertible. Then basically the rank of A is strictly less than n, and therefore the rank of AB is also strictly less than n. And the point is, whenever, so in other words, AB is not invertible. And in that case, what it means, we've shown that if a matrix is not invertible, the value of delta is 0. And if A is not invertible, the value of delta at A is also 0. So trivially, we have that delta AB is delta A times delta B, because both sides are 0. And now, if A is invertible, so I guess case 2, A is an elementary matrix. Let's say of type 1. So just interchange 2 rows. Then, if you interchange 2 rows of B, you get minus delta of B. But also, the minus is precisely this delta of A and delta of B. So it's true in this case. It's also true for the other types, based on those results above. And lastly, for the general case, just write A as a product of elementary matrices. Exactly like the proof of determinant of AB is determinant of A times determinant of B, then delta of AB, that's delta of EM, E2, E1, B. But the point is, this is elementary, and we've shown that for elementary matrices this is true. So EM, delta of the rest, EM minus 1, E1B, and then just continue like this, and you get delta of EM, delta of EM minus 1, delta of E1, delta of B, and then reverse this using the fact that each of those matrices is elementary, and you're left with our original matrix. Delta EM up to E1, delta B, and that's delta A times delta B. So it's a very quick proof, but again, because it's so similar to the previous result. And therefore, we have our multiplicativity. And lastly, we are actually now ready to do our proof. So now we can finally show that this thing is the same thing as a determinant. Well, case 1, if A is not invertible, we've shown that they do agree. So you see, we did all this work, now comes our reward. This is true. Case 2, A is elementary. Well, with those 3 cases, we've shown that in all 3 cases they agree. So in that case, delta A is also determinant of A. And lastly, general case. So because A is invertible, we can write A as a product of elementary matrices, E1. And then delta of A, that is delta of EM up to E1. And that is, remember, now we do have multiplicativity of delta. So EM up to delta of E1. But the whole point is, all those are all those matrices are elementary. So we get this. And lastly, determinants are multiplicative. So we get determinant of EM up to E1. But that's precisely the determinant of A. Big box. So in other words, we have shown that if A is any matrix, then delta, this mystery function, is just a determinant. which is really neat, and it sort of characterizes the essence of determinants. It's just any function with those three properties that is multilinear, that two adjacent rows gives you 0, and that delta at the identity is 1. By the way, if delta at the identity is not 1, you actually get just a multiple of the determinant. So then delta A would be delta I times determinant of A, whatever this value is. And I think it just follows, because then in this decomposition, or I guess no, in this above, I think the only thing that's different is like here we'll put delta i's. So delta I, and then just from recursively we get a delta I that pops out. Alright, I hope you like this determinant adventure. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.